If you read a paper about monetary economics or monetary policy these days, chances are that 1. The use of money is just assumed, if there is any money at all, and 2. Some sort of nominal rigidity is assumed. This means that prices aren't allowed to adjust in real time to changes in the economy. Arguably, both of these are ad hoc assumptions. Many economists might say that we know monetary policy has real effects, and we know that people use money, and we don't really care about the deep reasons behind any of this, so ad hoc assumptions that allow monetary policy to have real effects are fine. Anyway, if monetary policy is really about credit, we don't need to think about money at all. However, one could argue that the reasons why people use money and the reasons why there might be any nominal rigidities could be critical for how monetary policy works. As a result, other economists think it is critical to understand why money is used. Also, ideally we should be using models that have solid micro-foundations, not ad hoc models. Otherwise, why have economic theory at all? Today I want to introduce you to monetary search theory. Monetary search theory provides an underpinning to the question of why people use money. They do not have to use money. In fact, money is not something that they value at all. However, barter trade suffers from the problem that it can only occur if both parties have things the other party desires. In monetary trade, people might accept money in equilibrium even if they do not value it directly, because they think that when they find someone with their desired good, they will be at least as likely to accept money as payment as they are to wish to barter with them. Let's jump in. Alright, so to talk about monetary search, let's go with a simple version of the model. And perhaps the simplest is the model of Kiyotaki and Wright. So the key elements of this model are as follows. First, there is a continuum of agents of mass 1. Second, there is a commodity that comes in different varieties. Now we want an environment where people want to trade, so that means that people must produce one of these varieties, but they also must wish to consume a different variety. So agents like a proportion of the varieties of size X. If an agent consumes a desired variety, then they get utility U. Okay. Now, the agents live in a place I'm going to call farmland. And while they're in farmland, with probability alpha, they produce 1 unit of the good that they produce. And it's important in this model that agents can only carry 1 unit of their good, or of anything else actually, at a time. Now, an agent who has successfully produced can go to try and meet other agents to a place I'm going to call the market town. Market town is endowed with a matching technology, and what that does is that each period, if there are n sub m agents in the town, then beta times n sub m over 2 matches are made. A match is a pair of agents who get to interact. Okay? So what that means is the probability of me finding anyone is going to be beta. Now, as discussed, if you randomly pair two agents, the chance, the probability that one likes the good of the other is x, right? And the way I've described it, the probability that maybe both like each other's good is x squared. Let's just say that the probability that I like your good and that you like my good is independent, and then the probability is going to be x squared, that we both like each other's goods. Great. When paired, the agents can choose to exchange their goods or not. If they both do, then trade occurs, and if one or other of them doesn't want to trade, then there is no trade. So now we want to define an equilibrium, but I guess the equilibrium in this environment is going to be straightforward. An equilibrium is just going to be a situation in which agents are optimizing given what everyone else is doing, and that the population, in addition, in market town and in farmland will be constant over time. So let v sub 0 be the value of being in farmland, and v sub 1 the value of being in the market town. 0 indicates if you're in farmland, then you don't have any goods. 1 means that you produced a good and you're carrying it and you're looking to find a trading partner. Now, the following value functions I'm going to write down have two interpretations. One interpretation is that we are in continuous time. The other interpretation, as with search models in general, is that we are in discrete time, but I am measuring values at the end of the period, just before the agent goes to bed. So everything, all the payoffs that the agent is looking forward to are not going to happen until tomorrow, so everything is discounted. So suppose the agent, if we're in discrete time, has a discount factor of 1 over 1 plus r, or if we're in discrete or continuous time, we can just say that it has a discount rate of r. Then we're going to have the following. The flow value that an agent in market town, that an agent in farmland gets, is going to be alpha, which is the probability of anything changing in the agent's life, times, well, what's the change that could occur in their life? They could produce a good, in which case they are no longer in the market town, and so they lose that state. With probability 1 minus alpha, nothing happens, and so the flow is 0. What about if you're in market town? The flow that you get in market town, well, with probability beta times x squared, you meet someone who likes your good, and simultaneously you like their good. That's what's called a double coincidence of wants. I like what you have and you like what I have. In that case, what is the flow? Well, there's a direct flow of utility U, but also now my state has changed, so I'm going to get V0 and I'm going to lose V1. Now, with probability beta x times 1 minus x, I match with someone who doesn't like my good, but then nothing happens because we're not mutually willing to trade, and so you get 0, and the same is true of all the other outcomes outside of this one. So these are the value functions. Now there's one more object that we need to think about, which is that we would like to examine the flows between the two locations. If, let's say, n of f is the population of farmland and n sub m are the populations, then the number of people flowing out of farmland, well, it's a proportion alpha of them. That would have to equal the number of people flowing out of the market town, and that's going to be beta x squared times the population of the market. And finally, since we know that the sum of these two things has to equal 1, this means that in a steady state, if there is one, you're going to have the n sub f is beta x squared over alpha plus beta x squared, which of course is strictly less than 1. Great. So that's not very exciting because, of course, the agents just have to bump into each other. There are no decisions to be made other than whether or not to trade. But now you know what the environment is like without money. So now let's bring money into the picture. Suppose there is an additional object called fiat money. A fraction m of the population is endowed with it. This object, just like the goods, is not divisible, and just as before, the agents can only carry at most 1 unit of anything. So you can't have goods and money. Just like you can't have 2 goods or you can't have 2 units of money. The reason I called it fiat money is because the object that they use as money does not enter anyone's utility function. No one actually cares about money in the direct sense of deriving utility from it. However, it's there, and so agents may coordinate their behavior on it. And in particular, they may choose to give up a good in exchange for a unit of money. If they do that, then we would have an equilibrium where agents actually use money as part of their behavior, not because the use of money was assumed, but because the use of money is something that occurs in equilibrium. So let now V sub m be the value of holding a unit of money in market town. we're going to assume that people with money have no reason to be at the farm, since nothing happens at the farm that has anything to do with money. Let mu be the proportion of traders who have money. In other words, the proportion of n sub m that has money. So I guess maybe we should just write that out. That's going to be m over n sub m. Next, there's going to be one more object we need here. Let little pi, which we're going to bound between 0 and 1, be the probability that someone accepts money in trade, where this number little pi is a choice variable. In other words, if I'm in Market Town and I do not have money, I still, as a strategy or as an action, have a probability pi of accepting money if I bump into someone and they offer it to me. So the idea here is, of course, if I choose pi equals 0, that means I don't accept money. If I chose pi equals 1, it means I accept money for sure when it's offered. But we want to be careful. Maybe there's some interior probability that I might accept money. Similarly, let big pi be my belief, or an agent's belief, that if they offer money to someone, they will accept it. And of course, how are we going to define an equilibrium? An equilibrium is a value of big pi such that setting small pi equals to big pi is the maximand of the money holder's problem. In other words, if you believe big pi is the probability that someone out there will accept money from you, in an equilibrium we want little pi to also be the solution to the problem of someone who's deciding whether or not to accept money. Another way to put it is that we are seeking a fixed point of the best response correspondence, which is, given that there's people are playing big pi out there, what should I do? Any fixed points of that is going to be an equilibrium. So now let's solve this. And in this case, it's convenient to break this down into 3 cases. One case, let's say pure strategies. And the first case is going to be big pi equals 0. Second case, big pi equals 1. And the last case, mixed strategies. So that of course means pi is interior. However, it turns out that there is an easier way to do this. And the reason is going to be obvious once we start writing down their value functions. So let's do that. The form of the value function for the farmer doesn't change because you're just waiting under a tree for your variety of produce to fall on your head. Then you get to go to Market Town and you lose whatever you have in the farm. Now, suppose you have a good. Now, with probability beta, you're matched with someone, and conditional on being matched with someone, with probability 1 minus mu, that person doesn't have money. In that case, you barter, you get x squared, things are as before, you get to consume, and you're moving out back to the farm and losing your status as someone who had a good. But there is something else that can happen. With probability beta, you may be matched with someone who has money. With probability beta, you're matched with someone, and conditional on that, with probability mu, they have money. Now, this person is holding money. That means that they don't have any goods to offer you, but there is some probability x that they like your good, right? And if you were to accept it, if you were to accept their money in exchange for the good, then you would now become a money holder. You no longer be a goods holder. You would still be in Market Town. However, of course, the thing is, you may or may not want to do that. In fact, you're going to choose whether or not to do that. There's going to be this number pi here between 0 and 1, and you are actually choosing pi from the unit interval. Similarly, now we also have to figure out what's the value function of someone who has money, and the only interesting thing that can happen to them is that with probability beta they're matched with someone. If it's someone with money, then that's useless. They both have money, so there's nothing to trade. So then conditional on matching with probability 1 minus mu, the person doesn't have money. And with probability x, you like their good. Will they accept your money in exchange? Well, that happens with probability big pi. We don't know if it'll happen. But in that case, you get utility u. You leave the town. You don't have money. You just gave it up. And so you're gaining v0 because you're going to the farm, and you're losing vm because you just gave up your money. So these are the three value functions. Now, if you look at them, you'll see this is where someone without money consumes, and this is where someone with money consumes. If you look at these two expressions, you'll notice that they're exactly the same, except that this one has x squared, and this one has x times pi. So, suppose pi is less than x. If pi is less than x, then this times that is more than this times that, which means it's better to be a goods holder than a money holder. But it's strictly better to be a goods holder than a money holder. Then Vm minus V1 is negative, and so the agent would optimally set pi equal to 0. In other words, if big pi is less than x, then the optimal best response is 0. And that tells us one equilibrium, 0, 0, right? because 0 is less than x. That gives us a second equilibrium, because if big pi is equal to x, then this part here times u is equal to this part here times u, which tells us that Vm equals V1. And if Vm equals V1, then any pi is allowed. So if big pi is x, the best response is anything, and that gives us a second equilibrium, which is big pi equals x. And third, notice that if big pi is larger than x, then this times u is larger than this times u, which implies it's better to have money. Vm is strictly larger than V1. So the best response to any belief big pi larger than x is to set little pi equals to 1. That gives us our third equilibrium. Pi is 1. So, to sum up, we have 3 equilibria. The 3 cases that we talked about. Big pi equals 0, big pi equals 1, and big pi strictly equal to x. Excellent. And we did that just by examining the agent's best response correspondence, small pi, in response to any big pi. Now, to complete the description of the equilibrium, we would also want to solve for mu, which is an equilibrium object. Depends on the flows between market town and farmland, and on the size of the money supply M. But that's something that you could easily write down by yourself, and as explained, that doesn't affect what happens here in terms of the equilibrium. So it turns out this model has 3 equilibria, one where people don't use money. It's always going to be the case in a search model in general, if the money doesn't itself give anyone value. There are 2 monetary equilibria in addition to that. One, I guess, pure monetary equilibrium, where everyone uses money in all trades at every opportunity, except when they're bartering. And a mixed equilibrium where people sometimes accept money and sometimes turn it down. So you might wonder, aside from demonstrating what it means to have money being used as part of the equilibrium in this model, what kinds of other applications might there be? Well, one application that's in the original paper is the following. They say, suppose that x is a choice variable. What does that mean? It means, if you think about it, x is a chance that someone will like your good. So in a sense, it's a measure of specialization. So suppose if you decide to choose a smaller x, obviously it makes it less likely to find a trading partner. But let's say x also makes you more productive. Let's say alpha is a function of x, where the function a is decreasing. In other words, a broader x makes you less likely to produce, but a narrower x, you're more specialized, you're better at what you do, and so you are more productive. If you set up the same problem, you'll be able to find the same equilibria, pi equals 0, pi equals 1, and pi equals some interior value, but they show that the degree of specialization is greater if there's more use of money, which in a sense means that the economies with more use of money are also going to be more productive. So for that, you should go and look at the paper itself. Another extension is to try and make the goods divisible. And the next thing would have been how to make divisible money. There were several attempts to do this by Moliko, by Soyoung-shi, and I guess perhaps most successfully by Lagos and Wright. So if you're interested in this literature and seeing how it was extended to try and make this fairly stylized model look more like something you'd see in a typical DSG model or something like that, or RBC model for that matter, you should look at Lagos and Wright.